Dear audience, the title of my presentation is Towards a New Concept of Crack Path, a tribute to Jim Rice. I am Jesús Toribio and I am with the University of Salamanca, the oldest in Spain and one of the four oldest in Europe, Bologna in Italy, Oxford in UK and Paris in France being the other three. This is the beautiful logo of my university with the castle and the lion, Castilla and Leon, the foundation of modern Spain. The summary of my talk is 1. Introduction, 2. Experimental procedure, 3. Experimental results, 4. Discussion, 5. Conclusions. Let's go to the introduction. Motivation. Scientific interest, the study of the macroscopic fatigue performance of eutectoid steels and its relation with the microstructure. Importance of this study to analyze how the cold drawing process influences the fatigue microdamage in perlitic microstructures. The aims of the work, the study of the fatigue behavior of progressively drawn eutectoid steels, analyzing in particular the effect of progressive cold drawing on the crack aspect ratio evolution under fatigue. This is fatigue macro crack path. The effect of progressive cold drawing on the fatigue crack path at the microscopic level, it is fatigue micro crack path. Let's go to the second part, experimental procedure. Materials were perlitic steels with eutectoid compositions, approximately 0.80% of carbon and other elements. We deliver a cold drawing process from a hot roll bar, left-hand side, green color, 0 drawing steps, to the cold drawn wire, 7 drawing steps, to produce commercial prestressing steel wires, 1, 2, 3, 4, 5, 6 drawing steps. Microstructure of the hot roll bar, green color, left-hand side, and cold drawn wire, orange-red color, right-hand side column. While in the transverse direction both steels exhibit a randomly oriented microstructure, more closely packed in the cold drawn wire with curving of perlitic lamella, in the longitudinal directions, while the hot roll bar also exhibits a randomly oriented microstructure, the cold drawn wire exhibits a fully oriented and markedly oriented microstructure, the orientation being along the y-axis or cold drawing direction. With regard to the evolution of the stress-strain curve, sigma epsilon curve, we have this evolution, sigma epsilon, from E0, white color, to E7 in red color. There is a clear improvement of mechanical properties, yield strength and ultimate tensile strength as a consequence of the cold drawing process. Testing procedure, axial fatigue test in a universal testing machine, and we analyze the macro crack path by optical microscopy and the micro crack path by scanning electron microscopy and fractometallography. Experimental results, third part of the talk. Here we can observe the macro crack paths. In left-hand side, the hot roll bar, green color, and right-hand side, cold drawn wire, orange-red color. Both the hot roll bar, green, left side, and cold drawn wire, orange, right-hand side, exhibit an elliptical crack front. Then, regarding macro crack paths, here we can see for 1 drawing step to 6 drawing steps, the steel wires with an intermediate cold drawing degree exhibit retardation in the central area of the crack front due to the presence of compressive residual stresses in that zone. I call this Gould effect, retardation in the central area and quicker advance in the other regions of the crack. Regarding micro crack path, here we can see the hot roll bar and the cold drawn wire. Similar fractographic appearance of the crack path, resembling microplastic tearing for different drawing degrees. Again, regarding micro crack paths, The fatigue surface reveals a topography with striations. Secondary microcracks on fatigue surface, local deflections, branching, bifurcations, and so on. And again with the microcrack path, zigzag microcrack path with local microdeflections. Again, analyzing microcrack path in the horror bar at the top of the slide and cauldron wire at the bottom. For delta K, 50 megapascals per square meter left hand side to 40 megapascals per square meter right hand side. We observe an increase of crack path, microcrack path roughness for increasing delta K levels. The higher the intensity of fatigue loading, the higher the microcrack path roughness. And also there is a roughness increase of the microcrack path with the cold drawing degree. Then the cauldron wire exhibits more deflections, a higher roughness than the whole roll bar that is not cold drawn at all. Then the summary of conclusion regarding microcrack paths is as follows. Increasing number of microdeflections with shorter branch microlength and higher microdeflection angle as a consequence of the cold drawing process. This has four effects. 1, increase of the real fatigue fracture surface. 2, decrease of the fatigue crack growth FCG rate. Third, microstructure-induced fatigue crack growth retardation. And lastly, 4, drawing-induced fatigue crack growth retardation. Let's go to the 4-part discussion of the results. With regard to the microcrack path and the Gould effect, it is a consequence of the residual stress profile in the wires after cold drawing. We observe that residual stress distribution exhibits compressive area at the crack center and tensile area at the crack surface. The cold drawing process produces an axisymmetric residual stress profile, compressed at the center and tensile at the surface, thus influencing the fatigue crack front shape. With regard to the microcrack paths, we observe micro damage. Fractographic appearance resembles microplastic tearing, which is consistent with fatigue damage and crack advance developing by accumulation of plastic strain. The microcrack path in the horror bar, green color left hand side, and cauldron wire, red-orange color, right hand column. Fatigue cracks are transcolonial and translamellar. It is the crack path crosses the colonies and breaks the lamella. Fatigue cracks, the main cracks, exhibits a non-uniform COD and micro discontinuities, and secondary cracking appears in the form of local deflections, branchings, and bifurcations. The role of microstructure is as follows. Cold drawing process produces a microstructural orientation with microstructural elongation of perlitic colonies and lamella in the cold drawing direction. Here we have in the horror bar, green color, left-hand side, and cauldron wire, orange color, right-hand side. We observe that D7 is lower than D0. The micro deflection length decreases with cold drawing, but the micro deflection angle increases with the same cold drawing. Then D7 is smaller than D0, but theta 7 is greater, higher than theta 0. Then fatigue microcrack path in the cauldron wire exhibits more deflections and with higher angle. As a consequence, we do have a retardation of fatigue crack propagation. In a multi-scale approach, we analyze the key microstructural unit. We observe a decrease of perlitic interlamellar spacing and an increase of the angle, and microstructure which is progressively oriented and progressively densified, an increase of packing closeness with cold drawing, an orientation, in addition, an orientation along the drawing direction. The consequences in the fatigue crack paths in the horror bar green and cauldron wire orange. In the cauldron wire D7 we have shorter micro deflections and with higher angle, theta 7 higher than theta 0. Then, looking in the search of the key microstructural unit with these microstructural features, is 7 lower than S0, there is a decrease of pearlite interlamellar spacing and a progressive orientation, and we have a shortening of microcrack path deflections and an increase of micro deflection angle. Then the key microstructural unit governing the fatigue crack growth is the pearlite arrangement, the key parameters being both the interlamellar spacing and the pearlitic plates orientation, since the ferrite cementite interfaces block the dislocational movement, thereby producing a local retardation of the crack propagation. And finally, in this multi-scale approach, we observe the microcrack path deflection. Changes in cracking direction are frequently associated with changes in pearlitic lamellar orientation. Different colonies. Possible explanation: dislocational movement in ferrite lamella between cementate plates that block the glide. Here we observe the glide in the softer and more ductile ferrite phase, and this dislocational movement is blocked by the cementite harder and more brittle cementite lamella. Conclusions: fatigue crack propagation in eutectoid steel wires under tensile loading in the Paris regime develops in mode 1 with an elliptical crack front. The steel wires with an intermediate cold drawing degree exhibit a retardation at the crack front center due to the presence of compressive residual stresses in the central area of the crack front. Gould effect. The cold drawing manufacturing process improves the fatigue performance of eutectoid steel by retarding the fatigue crack growth rate in the Paris regime. The fractographic appearance of the fatigue cracks resembles microplastic tearing, which is consistent with fatigue damage and crack advance by accumulation of plastic strain in the vicinity of the crack tip. From the microscopical point of view, the fatigue cracks are transcolonial and translamellar. It is, the fatigue crack path crosses the colonies and breaks the lamella. The crack opening displacement is not uniform along the crack, and many micro discontinuities, branchings, bifurcations, and local deflections appear, the latter especially in heavily drawn steels. Thus, the cold drawing process produces a tertius crack path, a tertius microcrack path, so that the higher the cold drawing degree, the more tertius the propagation path. The key microstructural unit governing the fatigue crack growth is the pearlite arrangement, the key parameters being both the interlamellar spacing and the pearlitic plates orientation, since the ferrite cementite interfaces block the dislocational movement, thereby producing a local retardation of the crack propagation and the tertius crack path. Epilogue. The reverse approach to the concept of crack paths provides the idea of paths in cracks. We have crack in path and paths in crack, or paths near cracks, in the framework of the mathematical formulation of a path-independent integral near a crack tip, a path near a crack, and an integral whose value is independent of the particular path. So that this paper is a heartfelt tribute to Jim Rice and his J integral. And that's all. Thank you very much for your kind attention.